Okay, so this is college algebra. We are continuing our discussion of piecewise and power functions. We've actually finished piecewise, and now we're going to begin our discussion of power functions. A power function is a function that can be written of the form y is equal to ax to the power of b, where a and b are real numbers, or a, b are element of the reals, and b does not equal 0. So if we are squaring a function, okay, what we're saying is y is equal to x squared. All right, so 1 squared is 1, 2 squared is 4, negative 2 squared is 4. So this graph looks like a parabola. If we're cubing a function, y is equal to x cubed. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And this function looks something like this. Okay? If we have y is equal to x to the power of 2/3. So in other words, if I have a fractional exponent, okay, this is going to look something like this. All right, so let's graph that out. Okay, if we have y is equal to x to the power of 3/2, okay, this is going to look like this. Okay, so that's something like this. All right, so that's 3/2. All right, and then if we have y is equal to 1/2, oops, y is equal to x to the 1/2. That's going to look like this. All right, so x to the 1/2. And then finally, y is equal to x to the power of 1/3. So that looks like that. Oh, which means that I'm seeing that I did not. This needs to go through 1, 1. Okay. This is 1/3. This up here is not correct. Okay. X to the power of 3 does not look like this. It looks like this. There we go. Okay, so correct your top one there. All right, so here we've got our 4 graphs, and what we want to notice is, are they concave up or concave down? So we can see here that this graph goes out like this. This is concave down. This one, however, is like a cup. All right, so it's going to fill up. So this is concave up. Okay, again, x to the 1/2 is concave down. X to the 1/3 also concave down. All right, so what do we notice about the difference between the downs and then the up? Well, here our b, right, because these are of the form y is equal to ax to the power of b. Our b, or our exponent, is what determines whether it's concave down or concave up. Here our b is less than 1. here our b is less than 1. Here our b is less than 1, but here 3/2 is greater than 1. So we have a concave up graph. Let's examine the wingspan, okay, of birds. So this reads, at 17 feet, the wingspan of a prehistoric bony-toothed bird may exceed that of any other bird that ever existed. The animal weighed about 64 pounds and soared the Chilean sky 5 to 10 million years ago. The wingspan of any bird can be estimated by using the model L is equal to 2.43 W to the power of 0.3326, where L is the wingspan in feet and W is the weight in pounds. So we're going to graph this function in context of this application. So we've got 2.43, our W will be X, to the power of 0.3326. Okay. It says to use this function to compute the wingspan of a mute swan. If you want to read more about the mute swan, I have cut and pasted from the source, the most popular source of anybody who wants to be right, and that is Wikipedia. So read more about the mute swan. I want to compute the wingspan of a mute swan that's about 40 pounds. Well, I'm definitely going to need to adjust my window to say, let's say my x min is -5. My x max needs to be greater than 40. All right, let's let it be 50. Okay, and my y min, let's let that be -5, and my y max, let's let that be 20. Let's see what this graph looks like. So again, my window was x went between -5 and 50. My y was between -5 and 20. Now I can see the whole graph. Okay, if the thing weighs 40 pounds, that means that's my x. So I'm going to let x equal 40. Second calc value, 40. And I get that his wingspan is 8.3 feet. That's W. Okay? Or, sorry, L. This is my W. All right, now we're going to use the function to approximate the weight. So what I need to know is the weight, that's my x, of an albatross. If you're curious about albatross, I cut and pasted from Wikipedia, the official source of all things science, down at the bottom here. We're going to approximate the weight of an albatross whose wingspan, so that's L, is equal to 11 feet 4 inches. So how much is that in feet? Well, 4 inches is 1/3 of a foot. So we've got 11 and 1/3 feet. Okay, so I'm going to enter then into y2 because I need it to be my length. 11 11 and 1/3, oh crumbs, 11, why is that happening? 11, I'm just going to hit plus 1/3. Okay, so 11 plus 1/3 is 11 and 1/3. Let's see where this goes. All right, so I see that I'm going to need to extend my window. Let's let the x max be 80. Does that cover it? Not quite. Okay, let's let our x max be 130. Let's see if that covers it. I'm trying to adjust my window so that I can see the intersection. All right, looks like it's going to cross. So let's calculate our intersection. Second, calc intersect, enter, enter, enter. And I get that my intersection occurs at 34 thirds, right? That's my y, at 102.5 pounds. So that's the weight of a bird that has 11 1/3 foot wingspan. Okay, is the graph concave up, okay, or concave down? So we can see that it is concave down. And what that means is that my B, which is 0.3326, is less than 1. Okay. A root function is our functions with rational powers, okay, but they are not written in the form of fractional powers, but rather rewritten with a radical. So, for example, y is equal to x to the power of 1/3 can be rewritten as the cubed root of x. So what we drew then for the square root of x, or x is to the power of 1/2, is the same graph as y is equal to the square root of x. And then what we drew for y is equal to the power of 1/3 is the same graph for y is equal to the cubed root of x. So rational powers, in other words, fractional powers, can just be rewritten in the form y is equal to a to the nth root of x, where n is whatever the root is, okay? A reciprocal function, okay, is a function that can be written in the form y is equal to x to the power of -1. That's another way of saying y is equal to 1 over x. So we're going to graph y is equal to 1 over x. Let's see what this looks like. Isn't that interesting? Okay, so what we have formed here, let's hit second table and check out some guiding points. Okay, we've got -1, -1. Okay, we've got 1, 1, 2.5, 4.25. Okay, so this graph gets as close as possible to the x and y axis without even touching it. In fact, we see here on the table that at x is equal to 0, we get an error. Why is that? Well, if I were to plug in 0 in for x, I would get y is equal to 1 over 0. And that's undefined because I can't divide by 0. So what I have created here is a little graph that has what's called asymptotes. So this graph has both a vertical and a horizontal asymptote, which we will indicate by a dotted line. So we see that this graph approaches x is equal to 0 and y is equal to 0 as close as it can, but without actually touching it. So that's called an asymptote, an invisible line toward which the graph gets closer and closer. In other words, it approaches it, but it never crosses it. All right, so we're going to take a look at some other examples. namely 2x squared plus 1 divided by x. And let's see what this graph looks like. Very interesting, okay? So this graph, okay, let's get some guiding points here. Okay, -1, -3, 1, 3, okay, something like this, okay. All right, so these asymptotes, we have a vertical one here. So this is our invisible line that it approaches but never crosses, which makes sense. X can't equal 0, okay? But it also has what's called an oblique asymptote at y is equal to x. Okay, right, and I'm not going to make you know any much more than that. All right, let's take a look at the last ones. Check this out. All right, so we've got 2x divided by x minus 1. Okay, looks very similar to our parent function. Okay, it's a little bit shifted. Let's get some guiding points here. So we've got -1, 1. We've got at 1, we get an arrow, so that's going to be a vertical asymptote, which makes sense because if x were to equal 1, and we plug that in, we would be dividing by 0. And then 2, 4, 3, 3. All right, so our graph looks something like this. Okay, and so those are root and reciprocal functions, and then other functions with asymptotes.